So previously, we've shown that we can compute the likelihood of the parameters using the filtering algorithm, either the forwards algorithm or the Kalman filtering algorithm. And now what we're going to do in this video is concern ourselves with actually using that log likelihood to learn the parameters. And we're going to talk about a couple of different methods for doing this, at least at a high level. Now, at the top of this slide, I've written down the expression for the log likelihood and the fact that it's equal to the log of the joint distribution, marginalizing over the latent variables here. And we know for these latent variable models in general, one method we've looked at for learning the parameters is the EM algorithm. So we're going to sort of just sketch out what that would involve in the case where we have HMMs. So the E step's easy. In the E step, of course, of the EM algorithm, we take Q distribution over the latent variables, and we update it so that it is equal to the posterior distribution over the latent variables, given the observed variables and the current setting of the parameters theta. So this is the E step, and you can see here that this problem is solved by smoothing algorithms, either the Kalman smoothing approach, where you run the Kalman filter and the Kalman smoothing recursions backwards, or the forward-backward algorithm. That's something that we talked at a high level about a couple of video chunks ago. So E step is done. It's done by taking one of these standard off-the-shelf algorithms. Let's look at what was required for the M step. So the M step, if you remember, you can sort of check this by looking at the relevant video, updates the parameters by computing argmax over theta of the expected value with respect to the distribution over the latent variables of log of the joint distribution. This is what the M step has to do. And in the case of the types of models we've been looking at, this expected log joint here, this quantity in here, this thing is nice and easy. And one way of seeing that is if we considered our Gaussian model, for instance. So let's look at the linear Gaussian state space model, just as an example. This would amount to log of the product over T of PYT given XT, the emission distribution, which depends on parameters C and R, and then our dynamical expression, the transition distribution, P of XT given XT minus 1, and this depended on parameters A and Q, if you look back at the notes. So we need to compute the expected value of this quantity under Q. And we can take the product outside and rewrite this as a sum. And we can break the two terms up here. To be absolutely explicit, the brackets here in the log, of course, are around these quantities here. Let me do a less mangled bracket. This thing is the expected value over Q x1 to T of log PYT given XT, C, and R plus log P XT given XT minus 1, A and Q. Great. And now, to convince you that these expectations are simple to compute, notice that these things, of course, are Gaussian distributions. This is just a Gaussian in Y with a mean that was C times XT and a covariance R, and this is a Gaussian in XT with a mean A XT minus 1 and covariance Q. These are the expressions for the linear Gaussian state space model. And when you take log of a Gaussian, you're going to get a little quadratic form in XT in both of these cases. So that means when you compute these expectations, you'll need to compute the first order moments of xt, which is just the mean of xt, and some second order moments like xt times xt transpose and xt times xt minus 1 from this one. And that's all tractable. These are all things we know how to compute. So EM is tractable. It takes a little bit of time to derive it, but we could go and complete this derivation. We also said in the lectures on EM that EM tends to be slow. It performs these coordinate-wise optimizations of the lower bound or the free energy, where we first optimize Q and then we optimize theta. And that tends to work really badly if there's sort of strong coupling between Q and theta, like any coordinate ascent procedure will have that sort of pathological property. And so we're actually going to consider a second method here, which will improve upon it. So let's do that on the second slide here. So method 2 is going to be direct optimization of the log likelihood. What do I mean by that? I mean, what we're going to do is we're going to run some gradient-based procedure. It could be gradient descent, where theta nu is equal to the old setting of theta, plus some learning rate. Let's call this symbol. Give that symbol to the learning rate, times d log p y1 to t given theta d theta. So we're going to run gradient descent here to optimize the parameters. And this this term on the left here, I should make clear, is evaluated at theta equals theta old. So I haven't quite got space to write that in, but it's evaluated at theta equals theta old. Okay, so direct optimization is what we're going to do. And critically, these procedures like gradient descent, they're going to require access to these gradients. So we want to compute the gradients of the log likelihood directly. And what we're going to do is we're going to go through a neat little derivation to do this, which is kind of subtle. And we'll see that actually we have all the quantities we need to compute this derivative already too. In fact, it will depend on just on the sort of the Kalman smoothing recursions, and it will end up requiring very similar things to what we actually require in the M step. In particular, it will require gradients of this log joint probability in here. And that's just what we'd need to do to compute the M step. We need to compute gradients of this quantity with respect to the parameters to set them to their new values. And that's something we did for the mixture of Gaussians model. Okay, so let's, with that sort of in mind of where we're heading, let's run that through. So what I'm going to do to start with is I'm going to write down the gradient that we want to compute again. The gradient of this guy, and of course, that's equal to d by d theta of log of the integral p y1 to t x1 to t given theta dx1 to t. Great, so far so good. And now we can actually perform this derivative here. Notice I've written out everything into imagining we're doing integrals, i.e. we're in linear Gaussian SSM land, but you could replace the integrals with sums and be back to handling discrete latent variables and discrete hidden state HMM land. Okay, so this thing, well, we know how to differentiate logs. If you differentiate a log, you get 1 over the quantity. So 1 over, in this case, the quantity is an integral, p y1 to t, comma x1 to t, given theta, times by the derivative of the argument to the log. So here the argument to the log was that integral, so we have to differentiate that integral. So this is basic rules of how to differentiate the log function. Now I'm actually going to bring this derivative inside the log in here. And I'm going to use what looks like a weird trick. Okay, and the reason for using this weird trick will become apparent in a minute. What I'm going to do is, if we focus on this bit for the minute, I'm going to write this as integral d by d theta of exp log p y1 to t x1 to t given theta. So I've taken the logarithm and I've exponentiated, which would of course get us back to start with, which feels a bit weird. But the motivation here is partly because we want to identify this quantity, the log joint. That's going to play a central role in this derivative. It showed up in the EM, and so by applying the log and the exp, I've made sure that that same sort of term appears here. Okay, and I'm going to give it a shorthand just to make the equations a bit shorter. I'm going to call this E of y1 to t, x1 to t, and theta. Okay, it's just a function of theta, x1 to t, and y1 to t. Good, okay. And now we can perform this derivative. Oh, just one thing, I've forgotten the stuff out the front here. And the stuff out the front, if I actually put this integral back in, sorry, I missed this term out. If we do that integral, we of course get back to 1 over p y1 to t given theta. It's just the likelihood of the parameters again showing up at the front here. Okay, so a bit of jiggery pokery, and in a minute some magic stuff's going to happen. So let's write this out again. This is 1 over p y1 to t given theta. And now let's do the differentiation of exp of e. If you differentiate the exponential function, of course, you get the exponential function back, and you have to take the derivative of the argument to the exponential function and multiply that by the exponential. So here we'll get d by d theta of e differentiate the argument and multiply by the exponential function. Okay, great. All fine so far. And now we can notice something kind of neat. We notice that this term here is, of course, the exponential of the log joint. It's the exponential of this thing, which gives us back the joint distribution again. So I can rewrite this thing, p y1 to t, x1 to t, given theta. Okay, and this feels like we've gone backwards and forwards here, and are we really achieving much? But now we can take this thing out here that was multiplying this whole expression, and we can see that we can take it inside the integral sign because it doesn't depend on x. So we'll bring it inside the integral sign and collect it together with the joint distribution. So let's do that now. I'm running out a little bit of space, and I don't want to use a different slide so we can sort of see all the steps. So what I'm going to do is just erase this thing here. And I'm going to drop in the log joint here again and divide it by p y1 to t given theta. Okay, so it's taken that term out the front inside, so I can get rid of it from being outside here, and we get this expression dx1 to t. And the reason we've done that, of course, is now this term looks deeply suspicious. This thing here, if we apply Bayes' rule, is just probability of x1 to t given y1 to t and theta. It's the posterior distribution over the entire sequence given the observed variables. So we can rewrite this final expression here, we're almost home and dry, which I'm sure you're all glad, as an expectation over px1 to t given y1 to t and theta of the derivative of the energy function. What's the E? We called it E for energy. So in other words, the way that we get our gradients here of our log likelihood is we compute the log of the joint distribution, that's E, this thing we defined up here. And then we compute the gradients of that quantity with respect to each one of the parameters. And then we compute these expectations down here with respect to the posterior distribution over the latent variables. And this is extremely similar to all of the things we needed for EM. So if we go back to EM, you can see we needed the expected log joint here, where the expectation was over Q, and Q was previously updated to be the posterior distribution. And the way we would compute the parameter updates is, again, we differentiate this with respect to theta, which is exactly the same stuff that we need down here. So this is just as tractable as EM. It needs all the same things to be analytic. So it's simple to compute for, say, the linear Gaussian state space model. And so this then rather neatly gives us a method then for applying direct optimization of the log likelihood. It's going to require smoothing as an inner loop because you need to compute these expectations. But now we'll be doing direct optimization of the parameters, and this won't suffer from this problem that if the parameters and the Q distribution in EM are tightly coupled, then we get really slow convergence. Here we'll get quite quick convergence because we're doing full direct optimization of the log likelihood. Good. Okay, so big picture here is, sure, you could use EM to learn discrete hidden state HMMs and linear Gaussian state space models, but actually using all of the same bits of equipment, all of the same types of computation, you can actually do something rather faster and better in general, which is just direct optimization of the log likelihood using gradient descent. There's one final little detail that I've sort of glossed over, and that bit of detail is here we actually need more than just the basic Kalman filter expressions. Because of the term involving xt and xt minus 1, we need an additional expectation, which is not provided by the standard Kalman filter, which sometimes we get questions about. And that expectation is the expected value of xt times xt minus 1. But there's a special, again, recursive algorithm for computing this based on the Kalman smoother. And sometimes it's called the lag1 smoothing algorithm, lag1 smoother. So this is a detail that bothers people sometimes, but I wouldn't get too hung up about it. It's a sort of fairly trivial modification to the Kalman smoother. Great. Okay. This is the last bit about sequence modeling. So in the next video chunk, I'm just going to summarize what we have covered so far and talk about a few extensions and contextualize some of the topics that we've discussed as well a little more.